A Gallup poll of 1,487 adults showed that 43% of the respondents have Facebook pages. If appropriate, construct a 95% confidence interval for the proportion of adults who have a Facebook page. So you want to make sure that you check the conditions before you actually construct the confidence interval. So this statement, if appropriate, implies that you have to check the conditions. So the conditions are that n times p hat has to be bigger than or equal to 5, and n times q hat has to be bigger than or equal to 5. So we're going to go ahead and check both of these conditions. So let's go ahead and extract the information based on these two formulas. So we're going to need n, we're going to need p hat, and we're also going to need q hat. So n is equal to the sample size. The sample size is 1,487. And then p hat is the proportion of success or probability of success. In other words, it's the proportion of respondents that actually have Facebook pages. So in the example, it says that 43% of the respondents have Facebook pages. So then we're going to write this as 0.43. If the problem had given us a number, for example, if it said a Gallup poll of 1,487 adults showed that 43 of the respondents have Facebook pages, then p hat would be equal to 43 divided by 1,487. If the problem gives you a percentage, as it does in this case, 43% of the respondents have Facebook pages, then they're already giving us a proportion. Just write it as a decimal. So q hat is going to be 1 minus the p hat. To find 1 minus p hat, we're going to take 1 minus 0.43. So 1 minus 0.43 gives us back 0.57. So q hat is equal to 0.57. So we're going to go ahead and plug in the n, p hat, and the q hat into the conditions. So that's going to give us back 1487. Let me actually write out the formula. So n times p hat is equal to 1487 times 0.43. And then n times q hat is going to be equal to 1487 times 0.57. So this gives us back 1487 times 0.43, which is equal to 639.41. And for 1487 times 0.57, that gives us back 847.59. So both of these have n times p hat, n times q hat bigger than or equal to 5, which means that it meets the conditions, these two conditions, in order for this to be a normal approximation. So this just implies that we can use a normal approximation in order to compute a confidence interval for proportion. So again, this implies that we can use a normal distribution or a normal approximation. Technically, this problem follows a binomial distribution, but again, because it does meet the conditions, we can go ahead and use this normal approximation. So what does this mean in terms of formulas? In terms of formulas, that means that we can use a formula that has a z. So if you remember, the formula for constructing a proportion is p hat minus e to p hat plus an e, where e is equal to z sub alpha over 2 times square root of p hat times q hat over n. Or we can write p hat minus e is less than p hat plus e. So we can write it in interval notation, or we can write it in inequality notation. So what we're going to do now is we're going to actually compute the confidence intervals. If I go back to the condition, suppose that on a test it didn't meet one of the conditions, so one of the conditions fails, here we would say we cannot use a normal approximation, which would imply that you should not go and find the confidence interval. So if that's the case, then make sure that you write out the conditions, show how it fails, and then write a statement saying that we cannot use a normal approximation, and stop here. Do not construct a confidence interval. Because this one met the condition, then we can go ahead and construct the confidence interval. So in order to construct the confidence interval, we're also going to need, so based on the formula, we're going to need p hat, which we already have here. We're going to need q hat, which we already also have listed. We need n, which is a sample size. We already have that one listed. We also need z sub alpha over 2, which we're going to find in a second. Let me check the confidence interval formula. So we also need p hat, which is all of these. So we already found that one. So the only thing that we need to go and find is this z sub alpha over 2. So let's go ahead and find z sub alpha over 2. So for z sub alpha over 2, we have one of two options. We can either use the confidence level of 95% along with the critical values table. So we said the confidence level was 95%. That means that I can go ahead and use this part of the table to give me a critical value of 1.96. So this critical value is z sub alpha over 2 equals 1.96. So let's go ahead and go back to that example. So we said a confidence interval of 95%, or confidence level of 95%, is associated with a critical value of 1.96. So this is one way of finding that z sub alpha over 2. Another way of finding that z sub alpha over 2 is if you draw a normal distribution, again because the normal approximation was appropriate, we can use the formula with the normal distribution, which is z, which means that we draw the normal distribution, which is a bell shape. And this is a confidence interval, so that means that the middle is going to be the percent confidence. Percent confidence is 95%. That means that the rest of the picture is 5%. So if the whole picture is 100%, the rest of the picture, the shaded region in other words, would be alpha equals 0.05. So change that 5% into a decimal. This means that one of the pieces is going to be half of the alpha because it's symmetric. This piece on the left and the piece on the right side are going to be equal to each other. So we take half of that 0.05. So that means alpha divided by 2 is 0.05 divided by 2, which gives us back 0.025 for each of the tails on this distribution or on this picture. So then, because this is a z distribution, we would go to the z table and look at the area to the left of 0.025 to find the critical value on the left side. So let's look for 0.025. So if we go to the z distribution table, we're going to look for 0.025. So let's look at the first column. So usually I would suggest always starting on the first column and finding the number that's closest to 0.025 or the area that you're looking for. So 0.0228 and 0.0287 are close to 0.025. So if I go to the 0.0287, it takes me to 0.0281, 0.0274, 0.0268. So I'm getting closer, 0.0262, 0.0256, 0.025. This is the number that I was looking for. So we're going to go to the left of this value to read off the z score. So that's negative 1.9. And we're going to go up and meet that other part of the z value. So we get negative 1.9 and then a 6. So negative 1.96 is going to be the cutoff. So if we go back, that means that this number is going to be negative 1.96. if this is negative 1.96, this one would be 1.96 on the right side, and that's again because the normal distribution is a symmetric distribution. So then this value on the right is a critical value that we need, z sub alpha over 2, which is the same thing that we found using the common critical values table. So the common critical values table, by the way, you can only use it if your formula, if your margin of error has a z sub alpha over 2. If it had a t sub alpha over 2, you cannot use the common critical values table, and I'm referring to this table for the common critical values table. This again is only used for z sub alpha over 2. Alright, so going back to the problem, we're going to go ahead and find E, which is a margin of error. Margin of error is z sub alpha over 2, which we said was 1.96, times the square root of p hat. So p hat is 0.43, times q hat, which is 0.57, divided by n, and n is equal to 1487. And then we compute this on the calculator. So we get 1.96 times the square root, so go to second square root, 0.43 times 0.57, and then divide this by 1487. So this gives us back a 0.0252. So I'm going to use 4 numbers after the decimal just as a general rule of thumb, even though the book is going to have different rounding rules. So on the test, just go ahead and use 4 numbers after the decimal. So then we're going to go ahead and find p hat minus e, and then p hat plus an e to compute the values on the confidence interval. So p hat minus e is going to be 0.43, which was the p hat that we found before, minus e, which was 0.0252, and then p hat plus an e is going to be 0.43 plus 0.0252. So this is equal to, 0.43 minus, and we can scroll up to select the value that we need, and that's going to give us back 0.4048. And then if I do the same thing, we're going to type in 0.43 minus, and then, or plus I should say, so plus, and then we're going to scroll up to the value that we need, which was the margin of error, hit enter, and then hit enter again. So we get 0.4552. So the confidence interval can be written in one of 2 ways. You can write it in interval notation, or you can write it in inequality notation. So if you write it in interval notation, we're going to write 0.4048 to 0.4552, or you can write it in inequality notation, which would be 0.4048 is less than p is less than 0.4552. So you could write it in either one of these 2 ways, and both answers are completely accurate. You can write it again in interval notation or inequality notation. If you wanted to interpret the confidence interval, you can say that we are 95% confident that the interval from 0.4048 to 0.4552 actually contains the true proportion or the population proportion of adults who have a Facebook page. You can also interpret this in terms of percentages. So we can say we are 95% confident that the interval from 40.48% and 45.52% actually contains the true proportion or the population proportion of adults who have a Facebook page.